the most stable molecule is not always necessarily the major product. We have a diene here. When this is reacted with hydrobromic acid, it protonates the end of one of these double bonds. The result is a carbocation. The carbocation is delocalized over both of these carbons. These are half bonds. When this bromine ion comes in and reacts with the carbocation, there are two carbons that it can react with. Now, when thinking of which carbon it is most likely to react with, there are two different ways of considering this from what we know about carbocations and what we know about alkenes. The first thing one might consider is that this bromine is going to be more likely to react with this carbon right here, because this carbocation is more stable. There are two carbons next to it, whereas this N carbon here, there's only one carbon next to it. So therefore, since this is the more stable carbocation, it is more likely to react with this one. Another way of thinking about it from the perspective of an alkene is that this carbon is going to be more reactive, because when this bromine reacts with this carbon, the result is going to be an alkene. And if it reacts with this one, then the alkene is going to be on more substituted carbons. Here, the alkene will have two substitution groups, whereas if the bromine were to react with this carbon, then the only other carbon that this alkene would be bonded to is this one right here. So the double bond would be here. So bromine reacted here, the double bond would be here. If bromine reacts here, then the double bond would be here. This is a more substituted double bond, this is a more substituted carbocation. So it's a competition between these two things. And we'll have a look at how these two things play out. The first thing to notice is that at minus 80, the major product is the 1,2 product, the product where the reaction takes place on the more stable carbocation. So at this temperature, 80% of the product is the 1,2 product, and 20% of the product is the 1,4 product. At 40 degrees, only 20% is the 1,2 product, and 80% is the 1,4 product. Now, to understand the differences in the products, we have to look at the activation energies. So here's the transition state, or the intermediate, I should say, which is this right here. Let me get rid of all this other stuff. This right here. If we look at where it is on the energy diagram, it's right in the middle. Right here. Now on the energy diagram, the activation energy for the 1,2 product is smaller than the activation energy for the 1,4 product. Which means at lower temperatures, since this is the more stable carbocation, it's going to react more quickly. This reacts more quickly than this. Since this is more stable, it's easier for this to react here than it is to react here. And we can see that in the lower activation energy. So it's superficially more stable, but once the reaction has taken place and an alkene results, then this one is the more stable one. We can see here that it's more exothermic. It releases more energy when it comes down here. And the reason that this is a major product only at higher temperatures is because the reverse reaction is possible. So at low temperatures, this reverse reaction is unlikely. But at high temperatures, we can see that this can go back up to here, to the intermediate again. And at higher temperatures, while this reacts more quickly, there's some chance that it will return to this, and even though there's a lower probability of this product occurring, whenever this product does occur at higher temperatures, the activation energy is so high that it's not able to go back up. So whenever one of these things does form, it stays. So at lower temperatures, this is the dominant product. At higher temperatures, this is the dominant product. And this is because this reacts more quickly, but this is more thermodynamically stable.